Jai Hind everyone. I, Suvarna Mujumdar, Assistant Professor in Electronics and Communication Department, welcomes you in a lecture on timing diagram of 8085. Timing diagram is a graphical representation of the process how microprocessor work. It represents the clock cycle, the duration, the delay. It also shows about the content of the data bus, address bus, and what all the operation microprocessor is going to perform while giving executing any instruction. So if when we give an instruction to microprocessor, in case of 8085, we will take it as a timing diagram for 8085. Instruction consists of an opcode and operand. So time taken to execute a particular instruction is known as instruction cycle. So instruction cycle consists of the higher order address lines, the lower order data lines, address latch enable, read signal, write signal, and IO, input output memory. So whenever we draw the timing diagram for any instruction, we have to mention the data on higher order address line, what is the address on the address bus, data, what data that data line will carry, whether it is an opcode or whether it is an information or anything. We have to also mention about the address latch enable, the signal, that is the control signal. We have to mention the read, whether microprocessor is reading anything from the memory or input output devices, or whether microprocessor is writing anything in the memory. And finally, the input output memory signal. This is again a control and status signal which is used to specify whether microprocessor is working with memory or input output devices. So in case of instruction is nothing but a command given to a microprocessor that what all operation microprocessor has to perform. And program is nothing but a group of instructions. So whenever a microprocessor fetches one instruction from a memory at a time, it has to execute that. So instruction cycle basically consists of fetch cycle, decode cycle, and execute cycle. So fetching an instruction means reading that instruction from a memory. Then instruction decoder will decode that, and then finally the execution. Fetch cycle is nothing but the time microprocessor takes to read or fetch a opcode, that is operational code, from the memory. The timing to fetch any opcode is fixed. In case of 8085, the 4 T states are required to fetch any opcode. Now the execution cycle, that is finally after decoding the execution, the time taken for execution of any cycle depends on the length of this instruction, whether the instruction is a 1 byte instruction, 2 byte instruction, or 3 byte instruction. We will see in later how this instruction will affect the execution of the instruction. यार ये सफोकेशन के कारण हो रहा है क्या थोड़ा सा. Each instruction consists of some machine operation. So machine operation or machine cycle is the time required by microprocessor to execute particular machine operation like opcode fetch, memory read, memory write, IO read, and IO write. Whenever microprocessor perform any machine operation, it took some time, and the combination of these machine cycle will constitute a instruction cycle. As I told that microprocessor executes a machine cycle, each machine cycle consists of some T states. T states is nothing but the clock cycle. Suppose the frequency of microprocessor is 3 MHz, then 1 by 3 MHz is 1 T states. So number of T states required to perform any operation is your machine cycle. So an instruction consists of machine operation and the T states. This is the table which shows about the relation of the status signal. Whenever any operation is going to be performed by microprocessor, what is the outcome on the status signal? So there are 3 status signal, S1, S0, and IO/M bar. So these three status signals will gives us the status that whether microprocessor is doing opcode fetch machine operation or memory read, memory write, IO read, IO write or interrupt acknowledgement. So these are the operations that microprocessor is going to perform, and suppose microprocessor is going to perform memory read operations, then in that case memory is going to be executed. So this IO/M bar will be 0, S0 will be 0, S1 will be 0 and S0 will be 1. This indicates that microprocessor is dealing with memory and a write operation is going to be performed. Now, in case of opcode fetch, the instruction is, or we can say each instruction consists of opcode and operand. So, every instruction, whenever the instruction is executed, the first machine operation, it will be opcode fetch. And each opcode fetch cycle consists of 4 T states. So, this is the pictorial representation or graphical representation of opcode fetch. Address bus, higher order address bus will consist of higher order address value. T1 in T1 time cycle, lower order address and higher order address will be there. ALE signal will be high, indicating that buffer will or latch will latch the data, and read signal will be active low. Okay. So in T2 state, the read signal will be active low, and whenever this read signal goes active low, after that the data will be placed on the data bus. This data is coming from memory to microprocessor. Write signal will be active high because microprocessor is performing a reading operation, and the reading operation is going to be performed with memory. So that's why this memory signal will be active low. So this is the opcode fetch cycle for any instruction. This will be the memory read cycle. The time taken to perform memory read operation is 3 T states. So these are the 3 clock cycles. Address, higher order address will carry the address lines. ALE will be high. First T1 state, always in first T1 state, the ALE signal will be high, so that microprocessor gives a address on lower order address line, and that address will be latched by latch. So to give command to the latch, to activate the latch, ALE signal will be high. This is the status line. So as I told in the table form only, that if memory microprocessor is reading something from memory, then the signal will be low, S0 will be 1 and S0 will be 0. Read signal will be active low in T2 states, indicating that microprocessor is reading something from memory, and as soon as this read signal will be low, data will be placed on the data bus. In case of microprocessor is writing something in the memory, then again it took 3 T states. So in writing operation, address bus will be on address bus, ALE signal will be high, lower order address bus will be carried in T1 state, and the data will be placed by the microprocessor. So actually the data will be placed by microprocessor, so data will be placed within the T2 state starts, and then write signal will be active low, indicating that microprocessor is performing write operation. And IO/M bar will be low because the writing operation is performed with the memory. So these are the machine cycles which are used. Now we will see our example that when an instruction, that is move A comma B, this is a 1 byte instruction. It took only one location. The opcode is 78. So it is only one instruction, that is opcode fetch will be executed. So how it will work? The opcode is in memory and microprocessor has to fetch this opcode for decoding and execution. So for this will be the timing diagram. Microprocessor will place the address, that is A0 higher order address on address lines, lower order address 00 on lower order address line, and ALE signal will be high. After that, read signal will be active low. As soon as the read signal will be active low, memory will place 78H on the data bus. Write signal will be high and selection of this memory, that is IO/M bar, will be active low. Now the second example, that is MVI A, 45H. In this instruction, there are 2 cycles, 2 machine operation. One will be the opcode fetch. This is 3E is the opcode for MVI. So first this opcode will be fetched. and then the data will be fetched. This is the immediate data. This is stored in A0. So there are two operations. One is opcode fetch and next is memory read operation will be performed. So in case of MVI A, 45 fetch, two operation will be performed, two machine operation. First will be opcode fetch and next will be memory read. So total 7 T states are required. In first 4 T state, opcode will be fetched, that is 3E will be fetched, and after T4 time, T5, T6 and T7, 3 timing cycle are required for memory read operation. So first address bus, higher order address bus, lower order address will carry 8000H address. ALE signal will be high, read signal will be active low. As soon as the read signal will be active low, the data will be placed by memory on the data bus, and IO signal will be active low, indicating that operation is going to be with memory. After T4 time, again the address will be changed. So after T4 time, higher order address will not change, A0, but the lower order, that is 01, will be changed. This dash line, this is the high impedance state. This high impedance state is, this T4 time is the time taken by microprocessor to decode the 3E instruction. So 3E is the opcode. So this in T4 timing, the microprocessor will decode and get to know that now one more cycle is remaining. Execution is not over. It has to wait for 3 more cycles, and that is the memory read operation has to be performed. So after this T5, T6, T7, 01H will be placed on microprocessor lower order address line, and ALE signal will be again high and read signal will be active low. IO signal will be active low, indicating that memory is reading, microprocessor is reading from the memory. Now the next instruction, LXI H, for F045. So in LXI H for F045, here we can see that there are 3 machine operation, opcode fetch, 2 times memory read, because there are 2 data that are going to be fetched. One is 45 and one is F0. So first 45 will be fetched because it is lower order, which is stored at 01 location, and 02 location F0 will be fetched. So in this case, the timing required, the T states will be 10 T state. For 4 is opcode fetch, then 3 for memory read, and then 3 for again memory read. So here first higher order address will be placed, 00 will be lower order address, ALE will be high, read signal will be active low, and IO signal will be totally high because all the operation is going to perform with memory. After T4 time, microprocessor came to know that now it has to read 2 more memory location. So again it will go and give address 01 for second read option, 02 for third read option. And for these 2 read operation, again ALE signal will be high, read signal will be active low. When ALE signal is high, read signal will be high, indicating there is no operation is going to be. In T1 state, no read operation, no write operation will be performed. The read and write operation will be performed after T2 and T3 state only, because in T1 state or in the initial state, whether this is T5 or T8, these are the initial state of the next machine operation. So machine operation is changed from opcode fetch to memory read. So when the machine operation is changed, first T cycle is reserved for data or for address to be placed on the address bus. Now this is the instruction where we have to get a data for a memory location. Move A, M. This is a 1 byte instruction. Opcode fetch is the only cycle. But here the data is not in the memory. So it's not in the register. It's in a memory location. So we have to fetch a data from a memory location. So in this case, 2 cycles. 1 byte instruction, but it requires 2 machine operation. One is opcode fetch and one is memory read. In case of move M, A, the content of A to be placed in the memory location. Now in this case, the memory location, its address is specified by HL pair. So the content of HL register will become a memory location and there the data will be stored. Again, this is a 1 byte instruction, but it will take more machine operations. One is opcode fetch and another one is memory write. So first opcode will be fetched. 77 is the opcode will be fetched. Okay, it will be fetched from microprocessor memory to the microprocessor. Microprocessor decode it. Once it is decoded, it will microprocessor get to know that now it has to place the HL pair content as an address. So the content of H will be higher order address, will be placed on the higher order address line. The content of L will be placed on the lower order address line and ALE signal will be high, indicating now write operation has to be performed. So as the write operation has to be performed, so read signal will be high, but write signal will be active low, indicating that microprocessor is going to write something in the memory and memory signal will be high. Whenever microprocessor is performing any read or write operation with input output devices, then in that case everything will be remain same. Then only the content will be changed is this signal. This signal will be high, indicating that microprocessor is going to perform with memory. With input output device. So it will goes high when it has to be performed a read or write operation with microprocessor input output device. So in case of memory read or write operation, this will be the outcome. And in case of input output devices, the data will be, this signal will be changed here and it will be high, indicating that microprocessor is going to read something from memory. Okay, in this lecture we have covered about the timing diagram of microprocessor 8085. We have seen that there are different cases. It depends on the opcode fetch, memory read, memory write. All the machine operation will depend on the instruction which we are going to execute. So in case if there is a 1 byte instruction, it is not necessary that only the opcode fetch will be there. In case of 1 byte instruction, the instruction will depend whether the instruction needs more machine operation or only an opcode fetch machine operation. In case microprocessor has to read something from input device, then the condition will be input device IO slice M bar signal will be high, indicating that microprocessor is performing a input output machine operation. So if in case the signal is in 45H, then in this case microprocessor is going to read something from input device. Here the opcode will be fetched, this address will be fetched. So there are two machine operation, one will be opcode fetch, then address to memory read, and then the third machine operation. The third machine operation is IO read, because microprocessor has to read a data from this 45H location. This 45H is the location or address for an input device. So in this case, microprocessor first go and take data from memory, opcode fetch cycle, then memory read cycle, and then there is an input device. So microprocessor get read the data from here. So IO read operation. So there are three machine operation is going to be performed while executing in 45H. Similarly, in case of out 50H, it is a write operation that is going to be performed, and the write operation is with output device. So again in this case, the first will be opcode fetch machine cycle, memory read cycle. So microprocessor read this address, and the third cycle is IO write. So in case of IO write or IO read, the only option is the last IO/M bar signal will be high. Rest of the thing is as same as memory read or memory write cycle. Just we can have a recap for this timing diagram, how we are started and how we can draw a timing diagram for 8085 or any microprocessor. Timing diagram is nothing but a pictorial representation of the process that microprocessor is performing. So whenever a microprocessor is executing any instruction, it performs some machine operation. And we have seen the different machine operations are opcode fetch, memory read, memory write, IO read, IO write, INTA, interrupt acknowledgement, and halt. These are the some machine operation that specifically 8085 is performing. But these are the machine cycles which any of the microprocessor or microcontroller will be performing. In case of specifically if we deal with 8085, the first and foremost machine operation for any instruction is opcode fetch. Next, depending on opcode fetch, when this instruction is fetched, opcode is decoded, then microprocessor will decide which will be the next machine operation, whether it has to read something from memory or it has to read something from IO device or it has to write something. It all depends on that operational code, opcode, that is fetched and decoded. So we have seen different examples that like in MVI A, 30H, we have seen that this is the first opcode, then memory read operation has to be performed. If we write STA 3000H, then in this case first opcode fetch, then this memory read, again memory read and memory write. Fourth machine operation will be memory. So it all depends on the instruction to instruction which machine operation has to be performed. Now in case we have seen that in opcode fetch, the timing required to perform this opcode fetch is 4 T states. In case memory read operation is performing, it requires 3 T states, memory write 3 T states, IO read 3, again 3, and here we have different depending on which interrupts we are going to perform. So these are the timing required. So to calculate the how much time an instruction will took place while performing execution, from fetching, decoding and execution, we have to find the how many machine operation that particular instruction took place. We have seen for different variants, that we have seen for 1 byte instruction, that is if there is only an opcode, then that instruction is known as 1 byte instruction, and we have only opcode fetch. Example, if we can say complement CMA. So the opcode will be only fetched and opcode fetch cycle require 4 T states. In this CMA, the data will be in accumulator only and it get complemented and it will be stored. The reason why we have only one machine operation, because the data is in the microprocessor itself. In rest of the, for example, in this case, the data, this 30H, this data or we can say operand is in the memory. Immediate data, but it is stored in a memory. So microprocessor has to read the memory. So it has to perform another machine operation. So first machine operation is opcode fetch, next machine operation is memory read. In case of STA, first is opcode fetch, then microprocessor this instruction is store the content of accumulator in the location. So now microprocessor has to fetch the address where the data has to be stored from accumulator. So the address is again, this is the 3000 is the address which is in the memory. So the 3000 location, this 3000 has to be fetched by microprocessor, means read by microprocessor. So microprocessor will read one machine cycle, one read machine cycle, again machine cycle. So 2 read operation will be performed. Then my third operation, microprocessor has to write the content of accumulator to this 3000 location. So accumulator content, something is there. Suppose here we have 4AH. So this 4AH will traveling on the data bus and it will reach to the memory and it will be write in the memory. So the next machine operation will be memory write. So in case of STA, we have 4 machine operation. So it needs more time. 4 T state for opcode fetch, 3, 3, 4, 3. So So 10, 13 T states. So it required 13 T states to execute this particular instruction. So depending on the instruction, the machine operation will vary and signals will vary. So while defining each machine operation, we have to define the status signal accordingly while drawing the timing diagram. So status signals S1, S2 and IO/M bar. The value of these three will decide whether what operation microprocessor is performing. So in timing diagram, we are going to mention about address lines, the content of address line, the content of data lines. We will draw about ALE, address latch enable. We will draw about IO/M bar, that is control signal, S1, S0, read signal and write signal. So in pictorial representation of timing diagram for any instruction, we have to mention all these signals. Address lines again classified into two parts: higher order address line A8 to A15 and lower order address line A0 to A7 after latch. So we have to mention the data for these lines also. So in a timing diagram for any instruction, these are the important signals that we have to consider. In case of 8086, the timing diagram will be same. We have to again draw this, but the difference is whether microprocessor 8086 is working in minimum mode or maximum mode. Then in case if it is working in minimum mode, the timing diagram will be same as that of 8085, that is opcode fetch, memory read and memory write. But if it microprocessor is working in a maximum mode, that it is a master slave combination is there, and in that case we have to use a request and grant option, and then we have to design the timing diagram. So it will be little bit complex while drawing a pictorial representation for maximum mode, but if it is working in minimum mode, the same way we can draw the timing diagram for 8086. In case of 8051, the same process. Again, any instruction needs opcode fetch, memory read or memory write. Now in this case, in case of 8051 or microcontroller, the data will be in the internal RAM or external RAM or internal memory, ROM or external memory, or it all depends on the from where the microcontroller is fetching the information. So if it is dealing with internal memory, then it has to perform less instructions, but machine operation will be same, that memory read and memory write, but timing will be different. Okay, this is all about my timing diagram for microprocessor. Specifically, we have discussed about 8085, but we can use these concepts to design a timing diagram or draw a timing diagram for any of the microprocessor. Thank you.